Let's now do another example for the chi-squared contingency table. In this example, you'll see that the problem is set up in a similar way, in this case though, we'll have an expected value which is less than 5, and we'll need to combine to get rid of that. Alright, so the question goes, are all employees equally prone to having accidents, or are certain employee groups, say younger employees, more likely to have particular kinds of accidents? The effective implementation of hiring policies, training programs, and safety programs require such knowledge. A study was recently conducted to address these questions for a manufacturing company. The results are summarized in the table. Alright, so in the table we have kind of accidents, brain, burn, cut, and age under 25, and then 25 and over. Using a 5% level of significance, test whether there's a relationship between kind of accident and age. Actually, all the stuff in the beginning is virtually unimportant. What we really want here is the data, and to test whether there's a relationship between kind of accident and age. Alright, so let's write down our hypotheses. So, null hypothesis. There's no relationship, yet again. Between our two variables, we'll just say accident and age. Alternatively, there is a relationship between our two variables, accident and age. Right, no relationship for the null. Independence is a relationship. Dependence for the alternate. Alright, let's write up our data table. Alright, it's 4.5. Alright, so this is the cell smallest expected value, 4.5. I'll tell you now that all the other cells have expected values greater than 5. Let me fill those out quickly. Alright, so now you see that yes, in fact, the 4.5 is the lowest and only expected value which is less than 5. So we're going to have to combine in such a way that we can get rid of that. So in general, we either combine two rows, this row with another row, or this column with another column. In this case, we cannot combine the two columns because then we'd be left with only, we cannot combine the two rows because we'd be left with just one row, and then the degrees of freedom would go to 0. So what I'm going to do here is to combine these two columns, and so that we can have a functioning table and get rid of the 4.5. So when we're going to combine, we're going to go 17 plus 5 is 22 for the combined on the top row, and then 13 and 12 is 25, and then we'll have combined expected values. Let's fill that out now. Alright, so here we have our combined table. Alright, so as before, we combine the observed values. 17 and 5 is 22, 13 and 12 is 25, and either you can go 22 and 25 is 47, or 30 and 17 is 47. To get the expected values, of course, we go row total 31 times the column total 47 divided by the grand total 117, and the answer is 12.5. And same you can see for the result on the bottom right hand corner. Alright, so now we have all the expected values greater than 5. So now we're ready for the degrees of freedom. So the degrees of freedom is the number of rows minus 1 times the number of columns minus 1. Rows, we have 2 rows times, and then the columns, 2 columns now. So just like the previous example, 1 degree of freedom. Let's draw our chi-square distribution. Alright, so we'll use that to represent the chi-squared with 1 degree of freedom, alpha of 5%. So going back to the chi-squared tables, 1 degree of freedom, 5%, 3.84 for the critical value. Anything less than that, there's an insignificant relationship. Anything greater, we have a significant relationship. Okay, so let's write down our decision rule. Alright, decision rule. If the calculated value of chi-squared is less than or equal to the critical value, in this case 3.84, the observed and expected are close together, so do not reject the null. It's possible the null is true. As previously, we'll say there is a insignificant relationship between our two variables, accident and age. Alternatively, if the calculated value of chi-squared is greater than 3.84, sufficient difference between the observed and expected, we can reject the null and in its place accept the alternate. Right, and there is a significant relationship. Between our two variables, accident and age. Alright, so now it's time to do the calculated value of chi-squared. It's the summation of the expression observed minus expected squared divided by expected. So first cell 18 minus, first cell is 9 observed, 18.5 expected, so it's 9 minus 18.5 divided by 18.5. Alright, divided by 18.5, and we'll do that all the way down to the end, and the last one is listed at 25 and 34.5. So that'll be observed of 25 minus the expected 34.5. Square that difference, divide by 34. If we look at the calculation for the first cell by itself, 9 minus 18.5 divided by 18.5, you'll see that that's 4.88, which is already greater than the critical value of 3.84, so we really don't need to go any further. So we can go straight to a decision. Since calculated value of chi-squared is greater than 4.88, we don't know what it is since we didn't do the whole thing, so we put an asterisk on that. It's greater than 3.84, and we'll go back to our table and say that we did the calculation for the chi-squared for that cell only. It's a partial calculation. Partial calculation is greater than 3.84. Therefore, the total calculation must be greater than 3.84. So we can reject the null and accept the alternate. Alright, there is a significant relationship between our two variables, age and accident, or accident and age. Okay, and that's the end of that problem.